everybody, Sukanya here. Today we're going to be looking at the AP Physics 1 2025 version J, and we're going to be looking at question 1, which has something to do with momentum. So let's actually dive right into it. This question has, I believe, 3 parts. So we have A and then B. Okay, so it has 2 parts, but then part A has 3 parts. So essentially 4 questions, give or take. So let's honestly just get started. So we have a student has a cart of mass m subscript c, or just mc, and a block of mass 1/5 mc as shown in figure 1. All right, so the cart is of mc and the block is 1/5 mc. Okay, makes sense. And now let's read these 3 bullet points. So at time t equals 0, so I'm assuming we're looking at that part over here, the cart is moving to the right across a horizontal surface with constant speed. All right, constant speed. I know that basically just means acceleration is 0, and the student releases the block from rest. So they release it from rest, and it's going to the right at the speed vc, right over here. Now on to the second point. At t equals t1, so I think we're over here right now, the block collides with and sticks to the top of the cart. Collides with and sticks to the top of the cart. The block does not slide on the cart. Okay, the block just sticks and to the top of the cart, and it does not slide on the cart. Well, let's just ignore the second sentence for now and just look at the first sentence, because this is where most of the heavy lifting is. We see that it collides with, and whenever I see collides with, I automatically think, okay, this is a momentum problem. And it's really good to understand what type of problem you're working with so you know what type of formulas to apply. So automatically, I know that this is going to be something with momentum. I'm just making a few notes on the side. Momentum, and this other word, sticks. I know that when 2 objects collide with each other and they stick to one another, that is a perfectly inelastic collision. There are 3 types of collisions, and those are elastic, perfectly inelastic, and partially inelastic. But perfectly inelastic is the only one that has objects stick together. So we know we are focusing on the perfectly inelastic collision. All right, so I think that's all we can dissect from the second point. Let's go to the third point, which is from T2. At T2, the block cart system continues to move to the right, okay, with the constant speed Vf. So I think we're ready to go on to the first part. So the first part is on the axis shown in figure 2, sketch a graph of magnitude px, which is this part right over there, of the x component of the momentum. There we go. Now we definitely know we're talking about momentum. Of the block cart system as a function of time from t equals 0 to t is greater than t2. All right. Basically, what this question is asking us to do is just plot the x component of the momentum for each of these different time frames. All right. So let's start with the first time frame, which is between 0 and t1. I know that momentum right off the bat is equal to mass times velocity. So let me just scroll this up. So we're definitely going to be using this equation. And we're looking at this part right over here. So mass, at this point, we're just looking at the cart. The block hasn't been dropped on the cart yet. So the mass is just going to be mc, which is the mass of the cart. The velocity, they said, if I scroll up here, they said it was vc. So our momentum is equal to mc vc. All right, mc vc. And another point I want to note is that I know here momentum is conserved. And that is because I don't see any friction. I don't see any air resistance. There's no external forces outside the system. So I think momentum is conserved. And whenever momentum is conserved, I know that 0 to t1 is just going to be a straight line. And yeah, it's just going to be a straight line. And speaking of that, since momentum is conserved, I know that throughout this whole entire procedure, the momentum is just going to stay the same. So actually, this is just going to be a horizontal line of slope 0. Now we are on to A, part 2. So in order to solve this, it says derive an expression for the speed Vf of the block cart system after t equals t2. So after the block has been dropped on the cart already. In terms of mc and vc and physical constants as appropriate, begin your derivation by writing a fundamental physics principle or an equation from the reference information. So reference information, that means like the reference sheet, and then fundamental physics principle, we know that has to be something with momentum because we know this whole question is going to be about momentum. So it's asking for final velocity of the block after time is equal to t2. So let's just write whatever we know about momentum first. I know that this question specifically falls under conservation of momentum. So that means the initial momentum should be equal to the final momentum. And you can kind of see what I'm getting at over here. I know momentum in general is just equal to mass times velocity, right? So this initial momentum is when t is equal to 0, when we're just starting out. And this final momentum is going to be when t is equal to t2. So I know that the initial momentum is going to be equal to the initial mass times the initial velocity. So the initial mass times the initial velocity, and that is equal to the mass final times velocity final. And this is exactly what we have to find. And we actually know all the other constants because if we go back to our original problem, we already found the initial momentum right over here. We said that mc times vc, that's the initial momentum. So I'm just going to write that over here, mc times vc. Now I just need to find the mass final. And this is just some basic algebra. Mass final, we're looking at it over here. We know this is 1/5 mc, and we know this is mc. So we just add them, and that is going to be equal to 6/5 mc, and that is the final mass. So we have 6/5 mc times vf, and we're trying to find that. So I know that this and this cancel out, so vf is equal to 5/6 vc, and that is going to be our answer. All right, now on to the third part, derive an expression for the change in kinetic energy. Okay, so switching things up a bit. In the block cart system from t is equal to 0 to t is equal to t2 in terms of mc, vc, and physical constants as appropriate, begin your derivation by writing a fundamental physics principle or an equation from the reference information. So right off the bat, I know we're talking about change in kinetic energy. And I think to myself, you know what, that's actually true because in perfectly inelastic collisions, there is a change of kinetic energy. The initial kinetic energy is not equal to the final kinetic energy. So we're supposed to find that change in kinetic energy. So I know that change in kinetic energy is equal to kinetic energy final minus kinetic energy initial. I know kinetic energy final, the general formula is 1/2 mv squared, mvf squared, minus 1/2 mvi squared. And from here, these masses, once again, they're going to be different. Remember that. Maybe I should just do a final and then an initial right over there. So we found that the final mass is going to be 6/5 mc. And we found the final velocity from up here, and that is 5/6 vc squared minus 1/2. Initial mass was just mc because we just had the cart at that point. And then initial velocity was vc. Now, let's just solve this. I see that 1/2. So our final answer after doing that algebra is -1/12 mc vc squared. All right, so last part, consider the case where a new block is dropped and collides with the top of the cart. So I'm assuming we have the cart. I'm just going to say mc, might not be mc, but that's okay. And a new block is dropped. The new block slides along the cart during the collision, so it's like sliding along the cart, but does not slide off the cart. The time interval from when the new block collides with the cart and moves together with the cart is delta t. During delta t, there is a frictional force between the new block and the cart. Indicate whether the x component of the momentum of the new system increases, decreases, or remains constant during delta t. Okay, so let's simplify this a little bit. We have a cart MC and then something's blocked. A block is dropped on it, and we know that there is some frictional force happening between that block and the cart. And they're asking, is the x component of momentum of the new block cart system the same, decreases, or increases? And my thought process over here is that I'm thinking the momentum will only change if there is an external force, right? That's basically what we talked about in the beginning, because in the beginning we saw that there was no external force, hence conservation of momentum. But over here, I know there's a frictional force between the block and the cart, but that's the internal force. So this force over here, actually, that's confusing. But this frictional force over here is an internal force. I honestly think that the x component of momentum is going to remain constant, and just solely because of that reason. It's an internal force. It's not going to affect momentum at all. So a valid response I would write is that the x component Alright, so here is a rough explanation which would earn you the point on the AP exam. The x component of the momentum of the new block cart system would remain constant because the frictional force is an internal force, not an external force. Therefore, since there are no external forces being applied, the x component of the momentum stays the same. Hopefully you found this video helpful, and I'll see you guys in the next one.